Hey Team Bio, now that we've discussed this tricky light stuff, understanding the greenhouse effect and climate change is going to be easy. So just quick recap of this. We have a bunch of different types of light. We can only see the visible spectrum, but light occurs across all sorts of different wavelengths and frequencies, and they all have different properties. These different frequencies of light, and they interact with matter in different ways. So all materials, all matter is either reflective, absorptive, or transmissive of different forms of light. And depending on the material and depending on the wavelength of light, different things are going to happen. So you know that visible light cannot pass through a wall. It is transmission is 0 through a solid wall. However, wireless, which is another form of electromagnetic radiation or light, can pass through the wall. It is the wall is transparent to this type of light. Okay, so that's a big idea here, and it's going to help us explain why climate change is a thing. Okay, so here is a greenhouse. Some of you may have been in greenhouses before, and this will be familiar to you. Some of you have not, and this will not be familiar to you, but all of you have probably gotten into a car on a sunny day and found it to be much hotter in the car than it is outside. And so anytime I say greenhouse, you can just substitute the word car in, and it'll be the same logic. Okay, so we know that most of the light coming from the sun is within the visible spectrum of light. It is light that we can see, and I'm going to draw it. I'm going to try to draw it as yellow if I can figure out how to change the color. Here we go. So visible light from the sun comes into the greenhouse or comes into the car, and it does so through the windows, which we have picked this material glass because it is transparent to visible light. It allows it to pass through. So the visible light comes in and it hits something in the greenhouse, or it hits something in the car. Maybe it hits the seat of the car, or maybe it hits a plant in the greenhouse, and it is absorbed by either the car seat or by the plant in the greenhouse. Some of that light is going to be re-emitted by the plant or by the car seat. But now, instead of visible light, so let's label this. This is visible light. Instead of visible light, when this light is re-emitted by the plant or by the car seat, it is going to be in the form of IR light or heat. So just another form of light that in common parlance or everyday language we call heat, but is infrared light. So because these bodies, the car seats and the plants of the world are not as hot as the sun, when they re-emit light, it is heat, not visible light. And you all know that, where did this go? You all know that while glass is transparent to visible light, it does not let IR light to pass through. So the IR light bounces off the windows and stays in the greenhouse. Now, not all of it stays in the greenhouse. Some of it is going to pass through, but it will bounce a lot of the heat back. So what happens in here is that the greenhouse or the car heats up, because the light is trapped in this space. It cannot get out through the windows because it is trying to leave in a different form than it arrived in. Okay, so The same thing is happening on Earth with light from the sun. Very simplified model here is that sunlight comes down to us, and most of the sunlight that is hitting us, the sun is again emitting all different forms of light, all different wavelengths and frequencies of light, but the most prevalent frequency of light, the most frequent frequency, if you will, is visible light. And our atmosphere is mostly transparent to visible light. Not totally, actually about 30% of the light that hits the atmosphere is reflected off back into space. But this visible light that comes down and hits the Earth is absorbed by the Earth. And the Earth, again, a cooler body than the sun. When the Earth re-emits this light energy, it does so in the form of heat, or IR light. So some of this heat is able to escape from the atmosphere into space. But some of the heat is trapped by the atmosphere and re-radiated back into the Earth. Greenhouse gases like CO2 and methane and nitrous oxide, N2O, these are all greenhouse gases because while they are permeable, they're transparent to visible light. Visible light can pass right through them. They absorb heat light. They absorb light in the IR spectrum. And so as we add more and more and more CO2 into our atmosphere, the amount of heat that we are trapping, that we are preventing from escaping into space is increasing. Okay, so here we have to introduce another idea, which is the Earth's energy balance. Okay, the energy that comes into the Earth is from the sun. And this is a slightly variable number, but on average, it's about 340 watts per square meter. So you all have probably played around with light bulbs. 60-watt light bulbs, pretty standard size light bulb. A watt is a measure of energy, really. So the sun is shining on Earth, and on average, there's about 340 watts per square meter on every place on Earth. Although it's variable, you know that obviously the equator receives more energy than the poles from the sun. We talked about this. But if we were to average out over the whole Earth, this is what we get. Okay, so if the energy coming in from the sun is equal to the energy out, the energy that escapes as IR light or heat. Oops. So if this is true, if the energy in equals the energy out, then the Earth's temperature will be constant. However, the Earth will experience what's called a radiative forcing. If the energy in is not equal to the energy out. And as a result, the temperature will change. Okay, and to kind of explain this idea of temperature change of a body due to a radiative forcing, I think it's helpful to think of a cast iron pan on the stove. So before you light the fire underneath the pan, there's heat, all around the pan that is radiating out from every other body around it. And the pan absorbs some of that heat that's just in the environment, that heat light, and then it also radiates out some of that heat light. And initially, the energy in that it's getting from its surroundings is equal to the energy out that it's giving off to its surroundings. So its temperature remains constant. It's not getting hotter or cooler in this situation. However, as soon as we turn on the heat underneath the pan, now the pan is receiving more energy in than it's emitting out to its environment. And so the pan is going to start to heat up. It's experiencing what's called a positive forcing. So this happens when the energy in is greater than the energy out, and the consequence is temperature increases. Okay, the temperature of this pan is going to continue to increase and increase and increase and increase, and as it does so, as it gets hotter and hotter and hotter and hotter, it is going to start to emit more light energy in the form of heat as well. So you probably have experienced this if you've ever cooked food on a pan. As it heats up, your food cooks more quickly. So it's giving off, it's actually emitting more light energy, more heat energy as it heats up. So now we're going to reach a state where the pan is in radiative balance with the, it's in radiative balance just overall. The energy in that is coming from the flame underneath the pan is going to be equal to the energy out, the heat that's escaping from all directions from the pan. And then the pan is going to stop heating up. It has achieved energy balance. Now, when we turn off the flame, the energy that we're putting into the pan has now greatly decreased, but the energy that the pan is putting out into the world is still pretty high. So this is what's called a negative forcing. Now, the energy that is going into the pan is less than the energy that is coming out of the pan. And as a result, if the pan is shedding more energy than is being put into it now that the flame is off, the temperature of the pan is going to decrease. and the temperature of the pan will continue to decrease until the pan is back in balance with its environment. So the energy that's coming in from the environment, which just no longer includes the flame, equals the energy that it's putting back out into the world. So basically when it reaches ambient temperature of the room, it will be back in energy balance. Okay, so this is how all things change their temperature. If they experience a positive forcing, it means that the energy in is greater than the energy out, and their temperatures are going to increase. If they're experiencing a negative forcing, it means the energy that is coming in is less than the energy that's going out, and their temperature is going to decrease. So currently, the Earth is not in energy balance. Light from the sun is staying constant here, but the amount of energy that's able to escape into space has decreased as we've added more greenhouse gases to our atmosphere. And as a result, the Earth's temperature is going to increase until it's back in balance, which will eventually happen. And will happen faster if we stop adding greenhouse gases to our atmosphere. Okay, hope this was helpful in explaining the greenhouse effect and a little bit of basic science of climate change. I'll see you all in class tomorrow or the next day.